In this video, I'm going to try and get you started with the most challenging part of the assignment. That's the map raster. And I'm going to start by talking about some meta tips. So first, if you haven't done it yet, make sure that you do the thing mentioned in the previous video where you compile your code and you make sure you can get to this blank screen where you go to localhost 4567. Okay. The reason I'm asking you to do that now is because you want to do that as soon as possible while all the TAs are still around and while there's lots of resources. If you start at the last minute and you're having trouble even getting to this screen, you'll have a bad time indeed. Second, after you've done that, time to read the spec. So technically speaking, everything is there that you need somewhere in this spec or in the skeleton code. So you can, if you want, not even watch this video. This video is not required. It's just an alternate way of seeing things for those of you for whom this is useful. But read through the spec and get a sense for what the assignment's all about. Okay. Now, as you read it, you'll probably find there's a lot of little holes in your knowledge. That's okay. This video is intended to help fill those gaps. And you can either watch this video first or read the spec first, either way, but try to do both so you see everything from two different angles. Okay. Now what these slides here are, they're going to be posted in the spec and they'll just say what's in these videos. They'll give you a chance to read through the things I talked about. Okay. And throughout the assignment, I should also mention that you should always feel free to edit the code and play around with things, even if you're not quite sure what to do. Sometimes things like this are actually really helpful in order to figure out what is going on, right? And I'll talk about that in the next video. Okay. So I'll start by talking about rastering from a conceptual point of view so that you know what the goal of the problem is. So the first method that you're going to write is GetMapRaster. And at first it doesn't do anything and you're going to fill that in. And so let's see what it does. So the interface for this method is it takes something called params, and it's what the user wants in the map. It's going to be the region of the world that the user wants to see. And this method is supposed to return some kind of results that are going to capture the world, like a picture of the world. Okay. So it takes as an input a map here, and it produces a map. And all that stuff is described in the Java docs up here, but I'm going to go through it in words. So as an example, let's suppose that params is ullon -122.241, lrlon -122.240, and so forth. What this is saying is I want to see this region of the world given by these four numbers. We have ullon, which is the upper left longitude. We have the upper left latitude, the lower right longitude, and the lower right latitude. So it's actually just try visualizing these using Google Maps real quick. I think I already have it open. Yep. So I can go here and I'm going to put in the lower right coordinates. So longitude is our x coordinate. So -122.24053. And latitude is our y coordinate. And the reason is you can think of longitude as the x coordinates, your east-west direction, and latitude's your north-south direction. So if I type this in and I press enter, I get, I don't understand. That's nothing. So the reason is that common parlance is to put not the x coordinate first, but the y coordinate first. And that'll lead to a little bit of confusion in your lives, but hey, that's how it goes. So when I pick this coordinate, it zooms me over to here, and this is going to be the lower right coordinate of the map that I'd like to show. So whatever it is I want to show ends right there in the corner. Maybe it's that, maybe it's that, maybe it's that, who knows? Oh, sorry, maybe it's that, who knows? That's what the upper left coordinate's for. And I'm not going to go through that, okay? But that's just to give you a sense. I want to see a region of the world where this is the bottom right. Now, unlike Google Maps, where, look, I've just typed in an XY coordinate, you're not going to be serving, someone's not going to say, give me an XY. They're going to say, give me a box, and you're going to return that box. And we call that thing our query box, okay, because it's a rectangle. Or, yeah. Now, one of the assumptions we'll make for the assignment is that the world is flat, okay? And that's just how it's going to be because we don't want to take into account the curvature of the Earth. And it's just much easier if we think of longitude and latitude as just x, y. They're like perfectly beautifully orthogonal on a flat plane. Now there's other two pieces of information that are given to us, which are this width, 892, and this height, 875. And that is telling you how big the user's actual browser window is. It's saying this width is 892, and that's 878 in units of pixels. Now I'm gonna double check something real quick. All right, everything's good so far. Okay. I had to redo this video because of a dumb thing, so you got to see the recording software for just a moment. Okay, so to maybe consider this in a more relatable way, I'm gonna do a little conversion here. You don't have to know this fact to do the assignment, but I find it nicer to figure out what does it mean? What is a unit of longitude, right? When I say that I want to go between this unit of longitude, or this X address and this X address, let's say, how wide is that? Okay. So at our latitude, 38 degrees north, every degree of longitude is 288,200 feet. And it varies with latitude because as you go north, the Earth is smaller, right? In the sense that if you're at the 88th parallel, there's really not that much Earth at that latitude. So at our latitude, it's 288,200 feet. So when the user says they want a box that goes between this upper left and this lower right, that's going to be 317 feet, which I get by subtracting these two numbers in degrees of longitude and multiplying by this scaling factor. So in other words, if we go back to our little Google Maps example, it wants a box that's zoomed in so that each pixel is around 300 feet, which I happen to know from having done this video a couple times is going to be roughly this area of the world. That's what we're going to try and do. So one of the reasons that this number is particularly useful to us is it tells us that the user wants an image which is going to be around 0.355 feet per pixel. That is, if this is 892 pixels, it's actually a little more on my screen, and it's going to be, and I want 317 feet wide, every time I move my mouse, I want that movement of the pixel to correspond to 0.355 feet or around 4 inches. Okay, so how could that possibly affect you? What's up with that? So let me talk a little bit about the input files that you're given. So if we go to our input files, which were where? C users hug 61B temp proj 3. All right. So if I go there and I open up image, these are all the images we gave you. So these images are different in two ways. One, they show different locations, right? This is one location of Berkeley, but they also show the world in different levels of zoom. So this is some location in Berkeley, but far more zoomed in than these right here. And so what your program is basically going to do is it's going to take this sequence of information and it's going to find the best images from all of these sets, or all of these from among this entire set, and it's going to arrange them in a way that is optimal. Okay. So in other words, given this box, as I mentioned earlier, I want to show this region of the world. And so there's two requirements in order to decide how to do this. First, the images that you pick, let's say I pick just this one, they need to cover the entire query. That is, the part of the world that the user wants drawn must be drawn. Okay, that's simple enough. Second, if possible, you have to have sufficient pixels per distance in what I'm going to call LonDPP. That's longitudinal distance or degrees or longitudinal distance per pixel. So let's calculate that for the user's query. They want something that spans 0.0011 units of longitude, and they want it to be across 892 pixels. So ultimately what they want is an image resolution equal to 1.23542 times 10 to the minus 6 longitude units per pixel, or 0.355 feet per pixel, as we saw on the previous slide. So whatever images we pick better be that good. So let me give a little straw man example of a not so good choice. Let's say I just use 2.png. So there's two tests to decide, can I just show 2.png to the browser? Well, first, does it draw the entire query box? Well, it turns out that that little hook of the road is actually in this image. It's right around there, but it's too small to see. Okay. So if we consider that first thing, does it actually cover the box? Okay, this is me just drawing it in. The top left coordinate of this image is over here. The bottom right coordinate of 2.png is here. And so it includes the entire query box, and so it does actually pass this first test. However, it has a horrible resolution. So horrible, in fact, we can't see any of this stuff. Its LonDPP is 122.2558, that's this right here, minus 122.21191, divided by 256, which is 49 feet per pixel. Why 256? Like, why not 892? Well, it's because if we look at any of these images and we do file info, we see that they're all 256 by 256. So in terms of distance per pixel of this image, we need to divide by 256. In other words, if I move between two of the pixels, let me zoom real in so I can kind of see them. If I move from one pixel to the next, from there to there, that's going to be around 49 feet. Ooh, and I just rotated it. Oh, okay. 1, 2, 3. Okay, we're back. So that's 49 feet per pixel. That is much too low. We want 0.355. You're trying to give me 49. Okay, well, maybe I could do better. Maybe instead of 2.png, I'll use 21.png. And in fact, I'm going to show those real quick side by side. So that's okay, we got 2.png already open and 2.1.png. So if we compare these carefully, it turns out that 2.1.png is the top left corner of 2.png, right? So if we look here, it's like do 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 do. Okay, same deal. Do 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 do. It's a little slower, but it's the same song. It's the same shape, right? So this image, as it turns out, does also cover the entire query. There it is. And in fact, you can actually even see that crook of the road. This is only a very rough picture of showing it. But the problem is it's still way too poor of a resolution. We can again subtract these two numbers, divide by 256, and get 25 feet per pixel. That's not so good. So to test to see if this made sense, I want you to think about this. If every time I add another digit to the file name, I'm one more level of zoom, so that, for example, let's say 211. This is now the top left corner of the image we were just looking at. The question is, how many digits do I need in my file name so that we're finally good enough? And I'm just going to leave that open for you to ponder, and I will let you pause the video and think about it. Okay, so hint, the next one's going to have a resolution of around 12.5 feet per pixel. Okay, so it turns out that we can find a formula in here and say that the resolution, maybe resolution is a slightly abusive terminology now that I think about it, but the ln DPP is going to be 49 divided by 2 to the n-1, where n is the length of the file name. So for example, when n was 1, it was 49. When n was 2, it was around 49 divided by 2, and so forth. So suppose I had an 8-digit file. We'd get up to 49 divided by 2 to the 7th, which is 0.38 feet per pixel, which is still too coarse. The user wants it so that when they go 1 pixel over in the image, it corresponds to 0.355. This is too many. But when we finally get to n equals 9, well, in that case, we finally have a high enough resolution. It's actually even better than the user requested, but at that point, we've satisfied them. Now, as it happens, there are exponentially many images of a certain resolution. That is, if I add another digit, I have actually 4 times as many images. And so what will end up ultimately happening is I will run out of space. So we go up to 7 digits, not 9. And so we have a backup rule, which is, okay, well, if we get to the very end and we don't have enough room for all of our image, or so if we get to 7 digits, we still don't have a high enough resolution, we'll accept that, okay? So our rule is that if you can cover the user's query, do it. Otherwise, then we'll just do 7-digit files, and that'll be the best resolution we got, okay? So to summarize what we've got so far, we cannot use 2.png or 2.1.png. We need to use a longer file. We would want 9-digit file names. We don't have those, so we use 7, which is the highest resolution, the best level of zoom we have available. So let's consider this one, right? I'm just going to throw this out of nowhere. Could we use 2143411.png? Would that be allowable? Okay. So first we have to ask ourselves, does it cover the entire query? Well, we look at where the corners of this image are, and I'll talk about at the very end of this video how you calculate that. We look at the corner of these images and we say, does it cover the entire query? No, it doesn't. This is only the top left corner. So we need more images, actually, and typically that's how it's going to go. In fact, almost always, maybe always, you have to actually have many images together. So in this case, the query box is now larger than the PNG files of the appropriate resolution, and thus we're going to need to have more images. So I'm not going to go through the calculation of how you do that. That's part of what you have to think about. But it turns out that these 9 images shown here will fill out all the space. These 9 images cover the entire query box and then some. There's actually a little bit more covered, and that's okay, actually, by the way. Even though the user only wanted up to here, we're going to give them this little extra as a bonus. That's just how it is, okay? And that's fine. And so ultimately what we get is images that cover the desired range at least this resolution. We weren't able to do that because we don't have 9-digit file names, but these will work fine because this is the best we got. So that's ultimately what we got. Oops. Okay. So the last thing I want to say before I talk about how these where these numbers come from is how we return our result. Okay. So let's return back to code world. Someone tells us what box they want, and we need to return this image. But you'll note that this is not like a image type or something, or like picture. Instead, it is some map. Okay, what's that map? That's the question. Someone gives me a query, I give them back a map. Well, it turns out that map has to contain these exact 7 things. What are those 7 things? Well, they're listed in the Java docs here. This is the documentation. You need to return render grid, raster ul lon, depth, query success, raster lr lon, and so forth. And each of these have a pretty intuitive meaning if you followed all of this. So the raster ul lons and lr lons and all that, these are these 1, 2, 3, 4 numbers in red. Okay, that's what you return there. Depth is the length of the file name, how deep you had to go into what will probably be a quad tree, as I'll talk about in the next video. And then query success should be true if everything worked. And then the last thing you need to return is a string, a 2-dimensional string array that tells you which files go there. So we need a 2-dimensional string array where the top left entry is this, the next is that, the next is that. And so we'll have in total 3 rows, each of 3 columns, and that will give me what I want. And so ultimately, this information is all going to be in the map, or if we show a string representation of the map, including both the keys and the values, it'll look a little something like this. So in other words, someone gives you this purple map as an argument, you return this map as an output, and then the magical code renders everything nicely. So the last thing I want to talk about is this thing called file display demo. So what it does is, it's in the spec, it lets you actually see what each of the files corresponds to. So let's consider, for example, 2, the one we did here. I put in 2 and I do calculate. That tells me the coordinates of that tile, right? What it covers in the world, as well as its distance per pixel in 2 different formats. You got longitudinal degrees per pixel. You also have feet per pixel. We could do 2, 1, and we'll see that's the top left of that image. We could do, for example, 4, 1, 2, 2, 2. There you go. That's this image right here. And so ultimately, the way these calculations are done, your code's going to have to do this. In map server, there is the coordinates of the entire world. And because you know each time you go one level deeper, you're doing one of the corners, you can calculate. And that'll be one of the big challenges for you to think about. And that'll be more the next video. So that's everything you ever wanted to know about rastering. Perhaps it was a little too long, but that's the magic of 1.5x speed videos. Okay, so that's it. I'll see you in the next video and we'll talk a little more, but make sure that all of this makes sense. It's absolutely critical to get this before you start programming, otherwise you'll be a little doomed. The one thing you won't be able to do, by the way, is actually manually calculate these. This is too tedious because, well, there's bajillions of files. So the idea should make sense, but you shouldn't feel like you can carry out this calculation by hand. Okay, see you in the next video.